Hello and welcome to my channel. Today I'd like to invite you to join a journey to the center of the Earth. This is part one, so please do not forget to watch part two of this journey. And I admit, I borrowed this title from Verner's book written in 19th century. Verner's book is a novel fiction that doesn't reflect scientific point of view, even in 19th century. But the author imagination is incredible, really. But this title excellently fits to the subject of my presentation, taking you to visit the Earth interior. So let's start. The Earth interior is not a uniform body, but consists of some distinguished layers. Why? To answer this question, we need to back in time to the early stage of Earth creation. Briefly, because this video is not about Earth history, so simplifying as much as possible, the accretion process generated heat. That heat plus heat from radioactive isotopes caused melting or what is called partial melting of the accreted material. And the melted material was a mixture of heavy and light elements, also referred as the magma ocean. Thanks to the fact that the material was melted, the differentiation process was possible. It's easy to differentiate a melted material that behaves as fluid. To differentiate a solid material, it's been almost impossible. The rule of the differentiation process was simple. Heavier material travel to the center of the Earth, the lighter in the opposite direction. In that way, compositional stratification was formed. But please remember, the differentiation process was not a one-act process of accretion, melting, and differentiation overlapped. So if the planet was hit by another object, depending on its size and disturbance that caused the differentiation scale covered deeper just formed the interior structure, and it all also depended on how advanced was the differentiation process in the time of impact. For example, Theia, an object in size of Mars that led to moon creation, impacting proto-Earth, caused enormous disturbance and differentiation process scaled to the whole planet, almost resetting the existing structure. But what is the most important, that the chemical stratification affected physical properties of existing structure. Why? Now imagine if you have heavy and heavier materials moving towards the center, density of the material increases in the center. If the density increases, pressure is also increased. And we must remember that everything happened in the presence of heat extraction. And the combination of pressure and temperature and density determine the state of matter and the layers of the layers and the mechanical properties. So that's in short how the chemical and physical structure of the Earth interior was formed. Based on chemical properties, there is a metallic layer in the center of the planet core and silicate cover. The border at the depth of 2,900 kilometers is the most important border in the whole Earth, the Earth interior structure. It separates metallic interior from the rocky cover. Core is an alloy of iron and nickel and some light elements. The silicate cover consists of two layers. Mantle, that consists of heavy silicates, mostly iron and magnesium, and crust made of light silicates. Based on mechanical properties, there is a solid inner core, begins at the depth of 50 to 100 kilometers. Liquid outer core that begins at 2,900 kilometers. Stiff plastic mesosphere that started at 660 kilometers, and soft plastic asthenosphere, and pretty rigid, the most outer layer, lithosphere. Lithosphere and asthenosphere and mesosphere, they are in a solid state, although yeah, some of them are more plastic. But are you feeling at this moment that something is missing? I'm sure you heard the terms like upper mantle and lower mantle. So why are they not included here? If you compile both profiles of compositional and mechanical layers in the Earth interior, what's the result? Compositionally, it's the core, one layer. Mechanically, there is the solid inner core that and outer core that's liquid. And the result of that is that we have metallic solid inner core and metallic liquid outer core. And there is a similar situation with the next layers. Compositionally, there is the mantle, but mechanically we have mesosphere. And compiling these two layers, we have silicate stiff plastic lower mantle. But if you look, the mantle covers also asthenosphere and a part of lithosphere. So if you transfer the border of compositional mantle, we got the silicate rigid crust, the most outer layer, and silicate soft plastic upper mantle. But remember, comparing the thickness of lithosphere to the crust, we have a mystery layer. What's this? It's called uppermost upper mantle, uppermost upper mantle, or lithospheric mantle, and this part sticks to the crust. So that's why we have lithosphere as a one layer, because the crust and the uppermost mantle sticks together, so they create mechanically a one layer. And of course, remember the outer layers over the outer core are in a solid state of matter. And now you can ask me, how do we know it? Can we drill, for instance, to the core? Unfortunately not. The deepest ever made hole is Kola Super Deep borehole on Kola Peninsula in Russia. The depth of this hole is 12,262 meters. And if you compare to the radius of our planet, it's 0.2% of Earth radius. And the diameter of the borehole was only 9 inches. This is a fragment of the core from the drilling. The main goal of the drilling was to better understand the Earth crust. And the results were really impressive. because the drilling penetrated Baltic Shield and Precambrian rocks. The border between Proterozoic and Archean was determined at the depth of 6,842 meters. And if you want to know more about the geologic time, please watch my video, covers the subject. But coming back to Kola Super Deep hole, the drilling also showed that there is no transition from granite to basalt. It was expected based on seismic data at the depth around 9,000 meters, but there was still granite, but change under high pressure and high temperature conditions. Also, water was discovered in the lower depths. It was a mineralized fluid produced by pressurized flows of helium and hydrocarbons. Today, the site is closed. Due to technical and funds difficulties, the site was shut down in 1990s. And the only remnant over 20 years of drilling is the cap that covers the entrance to the deepest ever made true vertical well. There were some similar projects, but they didn't achieve 12,000 meters. There's also an interesting project called Moho done in 1960s. Although the depth wasn't impressive, 183 meters, but it was a precursor of deep sea drilling project and other continuation project. It also showed that drilling at the bottom of the ocean was possible. That was the base for oil company. And please remember, find the difference between the deepest and the longest. Because today the oil industry uses extended reach drilling that allows them to drill long holes, but usually horizontally. For example, the field in Qatar, the total length of the drilling was 12,290 meters, or the record of total length of 15,000 meters in Chevo field close to Sakhalin Island in Russia. But remember that it was not the deepest well, because the vertical part of this drilling was less than 1 kilometer. So please remember that the Kola Super Deep Hole is still the deepest ever made true vertical well. Some direct samples of Earth interior is provided by diamonds. Diamonds that reach surface thanks to kimberlite eruptions, and there are two types of diamonds: lithospheric diamonds and super deep diamonds. Lithospheric diamonds are formed at the depth of 150 to 200 kilometers below the surface. So it's pretty impressive. Please compare to the Kola super borehole, a little bit over 12,000 meters, so 12 kilometers. And so the diamonds gives, if they trap the water, they give us information about surroundings. In this case, the pressure that's still remaining in the trapped water. Similarly, super deep diamonds, they are formed below 200 kilometers, mostly below 410 kilometers. And also if the water is trapped, that give us information about pressure at that depth. And what is more interesting, and we are really lucky, the diamond can have a inclusion of surrounding minerals. And the first terrestrial observation of ringwoodite, a mineral that is formed below 520 kilometers, was found in a diamond from Huina, if I pronounce it properly. And it also gives us information that there is a lot of water at that depth. At this particular diamond, we found that there is 1.4 weight percentage of water, that it's 2.5 times more than Earth's ocean water on the surface of the Earth. The ringwoodite is a beautiful mineral, a little blue one. One of indirect methods used in Earth interior investigation relies on estimating the density of the planet as a whole planet, not only the outer layers. And the density of the whole planet is 5.52 gram per cubic centimeters. So comparing with the outer rocks density around 300 gram per cubic centimeters is much more. That means that there is something more dense inside the planet. Also, extraterrestrial bodies that hit our planet are also a good source of information of the Earth interior. How? For example, theorized existence of Bridgmanite was found in Tenham meteorite that fell in Australia at the end of 19th century. It is estimated that pressure and temperature during impact was identical to condition in Earth's mantle. So remember, Earth's lower mantle is at the depth from 660 to 2,900 kilometers. Also, conducting experiments and modeling gives us an idea what happened inside the planet. Especially so-called diamond anvil cell recreates high pressure and high temperature conditions, and using complex algorithms, we are able to simulate what is going there. Remember, so we are talking about deep layers, so it's possible to recreate conditions even in inner core, so below 5,200 kilometers. That's pretty deep, right? But real treasure for the Earth interior exploration, allowing us to look very deeply to the center of the planet, is use of seismic waves. There are two types of seismic waves, P waves and S waves. P waves are compression waves, also called primary waves, and S waves, shear waves, also known as secondary waves. So it's easy to remember. P, primary waves, S, secondary waves. P waves travel through fluids, but their trajectory is altered inside the outer core. That's why we have a shadow zone between around 103 and 150 degrees. S waves do not travel through fluids, so that's why we know that outer core is in a liquid state of matter. And there is a big shadow zone for this type of waves between 100 and 3 degrees. These properties of how seismic waves are propagated inside the Earth interior determines pattern of the per epicenter of earthquake and receivers. For example, if if we want to analyze inner core, we need epicenter and receiver in almost antipodal position. For example, South Sandwich Islands earthquakes recorded by the Ilson and Yellowknife in northern North America. Why? So please compare the depth of outer core and inner core, respectively 2,900 and 5,200 kilometers, to the radius, average radius of our Earth, 6,371 kilometers. Let's say we have a superset of seismic data. What now? Knowing the time of seismic waves are revolved from the epicenter to the receiver and the distance between epicenter and receiver, we can get velocity of the waves. Remember? P waves and S waves, and S waves doesn't travel through outer core. Observing how the velocity is changed with depth, it's possible to notice the depth on which the velocity changes drastically. It means the seismic waves penetrates a medium with different physical parameters, and the sudden change in parameters is known as discontinuity. And there is the first discontinuity is Moho discontinuity, noticed at the depth around 3 or to over 70 kilometers below the Earth's surface. And this two discontinuities at the depth of 410 and 520 kilometers. The discontinuity, also known as Gutenberg discontinuity, at the depth of 660 kilometers, and so-called Repetty discontinuity at the depth of 2,900 kilometers. There you know the number very well. It's the border between metallic and silicate layers in the Earth interior. And at the depth of 5,200 kilometers, there is a Lehman discontinuity. That's the border between outer and inner core. Recently is also noticed a discontinuity that describe 650 kilometers radius of so-called innermost inner core. We will talk about it in the second part of this video. And now, knowing the velocity, we can estimate density of medium that was penetrated by seismic waves. And knowing density and the depth and volume allows to estimate temperature and pressure. And now I give you a glimpse of how immense the pressure is in the Earth interior. Look at the surface is around 1,000 hectopascals. And if we travel to the center, it's around 360 gigapascal. So remember, 1 gigapascal is 10 million hectopascal. So the pressure is enormous. Now let's talk about each layer. So we have a mechanical layer, a lithosphere, and please remember from the very beginning we said that it's not crust, it's something more. Remember we compare compositional mantle and mechanical asthenosphere and lithosphere. and we create upper mantle. And from the upper mantle, we borrowed some part of it and stick to the crust, finding that it's uppermost upper mantle, also known as lithospheric mantle or just uppermost mantle. So remember, lithosphere is a crust plus uppermost upper mantle, and the border between them is Moho or Mohorovičić, the discontinuity. So please remember, Mohorovičić discontinuity separate crust from uppermost upper mantle, and together they create lithosphere. And now we know that the lithosphere is not uniform in the whole profile. To understand how lithosphere function, we can compare it with an iceberg that is partially submerged in the ocean. A lithosphere is submerged in the asthenosphere. So the submerged part of iceberg is partially melted. Water is trying to get deeper into the iceberg. Lithosphere part that is submerged into a asthenosphere is also a little bit melted. It is penetrated by surroundings, but it's still different from them. So lithosphere thickness varies, depends on type of the lithosphere, oceanic or continental. Continental lithosphere is always thicker. The oceanic one is thinnest in the ridges because there is the youngest lithosphere. If you look at the worldwide distribution of lithosphere thickness, you can easily determine the ridges, pink and white color, and the very old thick lithosphere and the craton of the continents. The density varies also according to preliminary reference Earth model. It varies from 2.6 to 3.4 grams per cubic centimeters. You know that 3.4 grams is in the uppermost upper mantle. So the below the Moho discontinuity. And speaking of Moho discontinuity, of course, the depth of Moho discontinuity varies, and it's always closer to the surface in the ocean areas, what we can see on this cartoon, and also on the worldwide distribution of Moho depth. And of course, the deepest Moho is under big mountain ranges in this case. And the differentiation of lithosphere is a key why on my diagrams lithosphere is with this angle, is shown with this angle, similarly crust and uppermost upper mantle. Now you know, because the thickness of the lithosphere is not the same all around the world, but is changed. One of the most impressive analyses of Moho depth was done by researchers studied Moho depth under North American continent. And what is noticed that lithosphere under Cordillera is up to 70 kilometers and up to 200 kilometers until Alberta and Trans-Hudson orogens, and almost 270 kilometers under Superior Craton. So the study shows that the Moho discontinuity, the depth of the Moho discontinuity reflects geotectonic, not topography. So Moho is remarkably flat, even in regions with substantial structural relief, 10 plus kilometers within the crust. And remember, structural relief is crust thickness, not altitude about sea level. So do not compare it with Mount Everest. Reasons for horizontal Moho can be that crustal roots are not formed beneath each orogeny, weak continental lithosphere during orogeny, or eclogitization of lower crust that is indistinguishable for seismic waves. Eclogitization is forming of dense rock at high pressure during tectonic process like orogeny. And in that case, petrologic crust boundary lies deeper than eclogitic metamorphic front. And sometimes nature offers us unusual opportunities to touch rocks created beneath Moho discontinuity. One of such locations is tablelands in Newfoundland in Canada. So if we are looking at the landscape and the geological profile, we can easily notice something strange, something different. How is it possible that the Earth's inner soul is exposed? Is an ophiolite. Ophiolite is a slab of oceanic lithosphere. So you remember very well that it's crust plus uppermost upper mantle beneath Moho discontinuity. And the slab was overthrust onto continental lithosphere. So this is this part of lithosphere on this scheme. And in reality, it's a little orange, we can say, because there are ultramafic rocks rich in iron. They are called peridotite. And you can observe that the Moho discontinuity in this area is between gabbro, you see the pale gray gabbro, and mafic and ultramafic rocks and the border between them. And this is not the only location. For example, in Oman, we have a Somile ophiolite. There is a very bold border between gabbro and Harzburgites. Harzburgite is a variety of peridotite, and the Moho discontinuity between them. Also, in Italy, in the Avria Verbano zone is known as a subcontinental petrologic Moho that you remember petrologic crust boundary always lies deeper than eclogitic metamorphic front, but the Moho discontinuity in this case is a border between gabbro and peridotite. So you remember that lithosphere is not uniform on its vertical profile. It's crust plus uppermost upper mantle and Moho discontinuity between them. We've just talked about it. But the most important thing is that lithosphere is not a solid lid at present days. It's divided into tectonic plates, also known as lithospheric plates, and they move in different directions, and they can be convergent boundary between them, divergent boundary between them, and transform a boundary between them. And the movement builds surface relief. So we have volcanoes, we have rifts, faults, orogens, etc. The movement is also a source of earthquakes. And fact that the lithosphere is not a solid lid it play a role in cooling system of the Earth. There is a still heat extraction from the center of the Earth, from the interior of the Earth. So we are at the border of lithosphere and asthenosphere. We will continue the journey, diving deeper and deeper into Earth interior in the next video. So thank you for watching this video. If you like it, please give me a thumb up and please subscribe. Both actions help me a lot. And please do not forget to watch the second part, Journey to the Center of the Earth. With geo greetings. See you in the next video.